Thank you very much, Professor Duarte. And thank you also for coming to my lecture. And I'm actually bowled over at the size of the audience. I'm maybe not so familiar with the topic of thermal comfort being so popular. And I think in many ways, some of the people that I've worked with in my career have abandoned the topic of thermal comfort because they think that all the problems have been solved. There's no more thermal comfort work needed. And one of the most famous people that I worked with, Professor Fanger, in my postdoctoral years in Denmark, he virtually walked away from the topic in the 1980s because he felt that finished, nothing more to do. So anyway, I'm delighted to see that there is so much interest still in this topic. I've been plugging away at it for 34 years, which is horrific when I actually do the tally, but that's actually true. I started in 1981 in my PhD and have just found so many interesting problems, interesting questions throughout that whole period. And most recently, I think the topic is getting more attention again because of what's going on outside of buildings. I think global climate change has really put a very sharp focus back onto this topic because thermal comfort is responsible for so much energy that's consumed in buildings. And with that energy consumption comes greenhouse gas emissions. So anyway, I'm delighted that the topic still has interest to so many people. I should introduce my co-authors. Cristina Candido is actually a Brazilian, so we have another connection to Brazil through her. She's from UFSC, is that correct pronunciation? UFSC in Florianopolis. And she came to do a joint PhD with me, what we call a co-tutel degree. And she actually has two PhDs, one from UFSC and one from Sydney, but both achieved in the same project. So I call her Dr. Christina. And Thomas, without the doctor, is one of my PhD students at the moment, Thomas Parkinson. And he's absolutely essential to almost everything that we're doing in the lab at the moment. He's my technical geek. He solves all of my problems with instruments and computing. And you'll see some of his work in this project in the questionnaires. So the topic that I'm going to talk to you about is residential thermal comfort. I think it's probably fair to say that overwhelming majority of work in this topic is done in commercial office buildings. We know very little about other environments, and we just assume that what's comfortable in an office building is comfortable in these other places. But I'm not so sure about that, and we'll have a look at some of the reasons why that's the case. And I've chosen this topic for Brazil. I've got a library of lectures I could have chosen, but I chose this one for a few reasons. One is that, and to be honest, my main motive for doing this talk here today is to maybe recruit some potential collaborators here in Brazil to apply the methods that we've developed in Sydney. Because I think Brazil is about to experience a growth in residential air conditioning. I've been having a discussion over lunch with Professor Duarte, and I got that message that it's starting to happen here. It's already happened in Australia, and it's starting to happen here. And the next stop on my what I call the Strolling Bones lecture tour is after Brazil is China. And I'll be doing this talk in China as well with the same intention, to recruit some collaborators there to hopefully apply these methods in a different cultural context and compare the results. I think it's going to be very interesting. So It's probably fairly accurate to say that there's about 100 years of research now in thermal comfort. And my contribution is just the last bit of it, or the last third of it, 34 years. But the topic goes back a long way before me. And really the beginnings of the scientific approach to thermal comfort work is related to the dawn of the air conditioning era. And there was the organisation that we know in America as ASHRAE. Its predecessors, ASHVAE, initiated this whole topic of research on thermal comfort to find out the answers to questions like, well, now that we've got air conditioning in buildings, what temperatures should we be running the buildings at? So it goes all the way back to Carrier. But as I said, overwhelming majority of the work is in office buildings, and maybe some other locations, relatively minor amounts of work, like healthcare environments, schools. We've been talking to some colleagues here about thermal comfort in schools, and educational environments, like this, for example. Thermal comfort in a lecture theatre is an interesting question, and we've seen some papers on that sort of topic. It's not just a question of thermal comfort, it's also a question of cognitive performance and learning, and what the relationship between that and temperature is. It's a very interesting mix, but relatively minor amounts of work on learning environments. And likewise, vehicular cabins. I've spent this morning looking at a very, very interesting research facility here at USP in mechanical engineering. It's a full-scale mock-up of the fuselage of an aircraft, of an airliner, and the question of thermal comfort inside aircraft cabins is of course very interesting. But again, relatively small amounts of work on transport or vehicular environments. And then another topic that is the subject of a discussion just over lunch, thermal comfort outside of buildings. And we talk about outdoors and semi-outdoors. Semi-outdoors being those interstitial spaces between outdoors and indoors that are partially built and partially natural. And so we generally, well, I have to say, in most of the literature on thermal comfort, you'll find an assumption that thermal comfort in one place is the same in all those other contexts. That I see repeatedly in research papers the assumption that the range of temperatures we find comfortable in office buildings is the same as the range of temperatures that we will find comfortable in semi-outdoor spaces. So it's a leap of faith that you can generalise the findings from one setting to all the others. And I'm not so convinced. I call that leap of faith deterministic logic. And it's, I think it's perpetrated mainly by engineers, and no disrespect to the engineers in the audience, but engineers tend to think of the human thermal comfort process in a deterministic way, that human beings are kind of like a thermometer, and if you put us into a thermal environment, we'll give a reading of discomfort on the scale, and that if you put us into another environment, we'll give another reading on the scale, just like a thermometer, and that we're repeatable, we're calibrated, and that everything works in a nice deterministic way, from physics through physiology, through psychology to behaviour. That's the assumption, but as I say, I'm not so convinced that it's so deterministic. So what I think anyway, one of the big missing pieces in the thermal comfort research literature is the residential sector. The residential sector. We spend a big chunk of our lives in our homes, and not much work has been done on thermal comfort in that context. We probably spend most of our lives inside our homes. I believe that, I predicted at least anyway, that thermal comfort results from a residential setting would be different from office environments. And I've got a few hypotheses as to why that might be the case. The first, of course, is in an office building, we really don't have what I can call adaptive opportunities. In an office building, we're kind of regulated in what we can do. Sometimes we're even told what we have to wear. In an office building, many commercial office buildings in my country have what we call a dress code. And you have to wear a fixed amount of clothing insulation. So not much adaptive opportunity. It's very rare to have a thermostat to control your own comfort. Sometimes you might be allowed to have a desk fan, but it's, again, fairly uncommon. And so in research terms, you'd say that the office environment is a very uniform, regulated sort of setting. Residentials, houses, on the other hand, are deregulated. The occupant can adapt in a variety of ways. So that's one good reason for thinking that they might be different from offices. Clothing patterns obviously are going to be different, dramatically different from residential compared to office. Another big difference, in my country at least anyway, is the cost of energy. In an office building, in the workplace, the energy price or the energy cost is borne by the boss, by the employer. But in the home, the cost is borne by the occupant, by the resident. They pay their own electricity bills. So when they turn on that air conditioning system, it's their money that they're spending. It's not the boss's. And so I expect that might have an influence on thermal comfort as well. And then, of course, finally, the occupants' activities in residential settings are going to be quite different to what we find in an office context. So that's one aspect prompting my interest in this setting. Another aspect of it is, or another reason why people haven't really looked so closely at residential comfort yet, is that in an office environment, we typically have to provide one temperature for many people. And so there's a research need to know what that temperature should be. In the residential setting, there's no need. The occupant can decide themselves. They can adjust their own temperature, and it's their choice. So there's no standardization requirement for residential. So there's not so much research on this. Now, having said all of that, there are other reasons why we should be interested in thermal comfort in residential settings. And well, I could say that there's been significant policy reasons for this new interest in residential thermal comfort. And the two obvious ones in my country, and I think that these might be relevant in the Brazilian context as well, but perhaps the first one lesser, not so important here in Brazil, is the greenhouse gas emissions that are connected to residential air conditioning. In my country, there's been a phenomenal growth in air conditioning penetration of the residential sector. At the moment, it's standing at about between 60 and 70% of homes would have an air conditioning system. Most of that equipment would be of the split system type, where you've got a separate external compressor or air conditioning unit and the internal delivery. But a very small market segment would have centralised air conditioning, where there's a large central plant supplying multiple rooms. So phenomenal growth in air conditioning in residential sectors in the last couple of years, and to be honest, the growth has really taken off since about 2000. Since about the year 2000, the penetration of air conditioning has gone dramatically up. And there's a variety of reasons for that, but probably the most important one is the fact that the equipment, air conditioning equipment itself, has become very cheap. in my country, very cheap. And it's all, of course, sourced from China. We have a market that's been flooded with very, very low-cost equipment that everybody can afford. So the uptake has been quite dramatic. So that's one aspect of it, the greenhouse emissions related to that consumption of electricity. Another reason why the topic is just getting a lot of policy attention at the moment is the impact of all that residential air conditioning equipment on the electricity grid. In my country, we have an electricity grid that's dominated by thermal coal-fired plants, and we have a fairly spiky sort of demand profile. And the peak demand, the highest demand for electricity always occurs on heat wave weather conditions. Whenever the temperature of Sydney, for example, gets into the high 30s, you will see a very, very dramatic increase in electricity demand, a spike in electricity demand, and that puts a real burden on the grid. And if there's a heat wave in Sydney and in Melbourne and in Adelaide all together, then we could seriously have blackouts on our grid because the demand exceeds the supply. So the response to that is build more power supply. Unfortunately, that's the way that's the logic of the policy at the moment. If we have a spike in demand, we just have to build capacity to deal with that. So we're building more and more power plants to be used during these very, very isolated occasions of heat waves, maybe 5% of the year. So we spend billions of dollars and use it for 5% of the year. And the rest of the time, that infrastructure is idle, and it's completely, it's a waste of money. So this is another reason why I'm finding it kind of important to investigate a little bit more the residential air conditioning, because the reason for that spike in demand is that everybody rushes home after work and turns on the air conditioning system all at once, and the grid just can't cope with it. Still talking about policy and how policy relates to all of this, one of the interesting examples of how little we know about thermal comfort in residential settings was discovered by my federal government in Australia. A couple of years ago, they had a policy to give away home insulation, to literally give householders free insulation to put in the ceilings of their homes. Why would a government be doing that? And the answer was, well, it was a policy designed to reduce our national greenhouse gas emissions. And the logic behind it was that if we give thermal insulation to houses, they will have comfort at lower energy requirements because the thermal performance of the envelope is going to be superior. That was the logic, and I call it an example of this deterministic comfort logic that unfortunately was fatally flawed. But I've described the logic here as a Boolean statement. The policy was based on this assumption that if comfort stays constant and the housing thermal performance, the envelope thermal performance improves because of better insulation, well then electricity demand should reduce. And it seemed like a logical sequence of steps. But that's not what happened. In actual fact, something quite perverse happened in response. Because what happens was the thermal performance of the housing improved, but the comfort also improved. People would spend the energy savings to enlarge their comfort footprint. So instead of just making comfortable one room or two rooms, now they can make comfortable all of the house. And so they turn up the equipment and get more comfort. So contrary to the expectations of the policy, the actual energy consumption didn't drop dramatically at all. It dropped a little bit, but people's behaviour actual behaviour defied logic. It went in a reverse way. So the behavioural economists call this the rebound effect. And there's been a lot written on it, and it's a fascinating topic in itself. It's, I can give you some more detail, a more formal definition of the rebound effect. But it's about human behaviour, and that it can be defined as the behavioural or other systemic response to the introduction of new technology that increases the efficiency of resource use. The behavioural responses tend to offset the beneficial effects of the new technology. So as a result of the rebound effect in the residential setting that I was just describing to you, the actual electricity or greenhouse gas savings are significantly less than the savings calculated by the technocrats using deterministic comfort logic. So the government got burnt. The government got its fingers burnt with that policy. It spent a lot of money and it didn't get much benefit in terms of reduction in greenhouse gas. So, there's a lot of good reasons for exploring residential comfort in more detail. And you have to ask yourself the questions, well, I certainly ask the question, why other people haven't done this before? Why hasn't there been a lot of work on thermal comfort in houses before? And the only sensible answer that I can come up with is that it's hard. It's actually too hard, really hard. It's easy to do thermal comfort in a lecture theatre. This would be a piece of cake. I would simply set up a piece of equipment in the middle, measure temperature, measure air movement, measure the radiant loads, and measure humidity, and then quickly distribute a questionnaire to all of you, and I would get probably 60 to 80 responses in a flash. If I wanted 60 to 80 responses in residences, I would have to knock on 60 to 80 doors and ask for permission to come in, which is not going to happen anyway. They're not going to let me in the house. And if they did let me in the house, it would cost me half an hour to an hour just to get one vote. And then I'd have to move to the next house and knock on the door, and you can see that it's going to be really, really tedious and time-consuming. So therein, I think, lies the problem, that it's just too hard to do this in residential settings. There have been a few studies. I won't go through these in any great detail, but having read the literature myself, I'm not satisfied that it's been done all that well. So we've got a new approach. We've got a new approach, and we're very, very interested to see if we can use our new approach in different contexts. And the core of the approach, the new method that we've got, is really based on the smartphone. This ubiquitous technology that we've all got in our pockets now. It's absolutely everywhere. I'm sure everybody in this room has got a smartphone now, or at least 95%. And it occurs to us that this is the way to do it. This is the way to do it. You don't need to go into homes every time you want to get a thermal comfort vote. You just use this. This is the way forward. So in Australia, it's 84% of the population has a smartphone. And it's rising to 100%. It's interactive, it's nice and quick. Another feature of the smartphone that is really working in our favour is that it's always on. It's always on. People start sweating if the phone's battery is getting low. You know, they panic. I've seen in taxis in Brazil that there's a charger in the back seat. I've never seen that anywhere else. So I think Brazilians are as addicted to these things as we are, if not more so. So it's always on, and here's the great thing about it, it's always on us. It's always with us. People take these things to bed. People sleep with their phones. They do. They text messages in the middle of the night. Crazy. You take them to the bathroom. So It's a fantastic research tool that hasn't actually been used yet. So, and another beautiful thing about them is this dot point that I call footloose. Well, the idea of using technology to deliver questionnaires is not new. That's been around for a long time. But this computer is a footloose computer in that it doesn't require the occupant to get up and move to a desktop or even a laptop. It's going to be with them wherever they go. And there's no how would you put it? There's no impediment to them responding. If I got a request to go and do a thermal comfort questionnaire, but I had to get up and go to my study where there's another computer, I'd say, I'm not interested, I'm watching TV and I'm not going to do it. But there's no excuse because this thing is with me all the time. So this is where Tom comes into the project. My co-author, Thomas Parkinson, we developed this technique. We call it Comfort Chimp. And it's a reference to a questionnaire service that's been around for ages on the internet for free called SurveyMonkey. Has anybody heard of SurveyMonkey? Yeah, it's a free, you can design electronic questionnaires and distribute them for free. It's a very nice facility. So we wanted to come up with something different, but something similar as well, so we called it Comfort Chimp. And it works like this. We have an online control panel. It's basically a software that we've written that enables us to customize the questionnaire, and a battery of questionnaire items that we can select from. It's like a wardrobe, a menu. We can pick and choose which questions go into the questionnaire, very easy. It enables us to convert from one language to another. So obviously in my country we're going to develop the questionnaires initially in English, but the next language is Chinese. So we've got Chinese versions of our questionnaire, Mandarin. And then, of course, hopefully, if we can get some interest here in Brazil, we'd have a Portuguese version quite easily as well. So the questionnaire is developed in our lab on screen, and then we distribute that questionnaire to the respondents, to the household respondents. So we've selected a sample of people to participate in the project, and we have their phone numbers. And we simply send a text message from our server through a gateway, through an SMS gateway, to those phone numbers. And it all happens very, very quickly, and very importantly, it happens very, very cheaply. It costs us just a couple of cents to send that text message to each person. And the couple of cents applies whether they're in Australia, or in China, or in Brazil. It's the same price. So we can do this anywhere in the world. We can do this in Africa. We can do it in Japan. It's no problem whatsoever. So it's a very simple technique. So once the text message comes into the phone, the respondent clicks on it, and it takes them to a web page. And then that web page is the questionnaire, and they can do that. So on my next slide, this is the bit that I'm always nervous about because sometimes it doesn't work, but it should if everything goes well. So this is what the questionnaire actually looks like on the smartphone. Oh, sorry, what have I done? Text message comes in, tells the owner who we are. There's the link. Click on the link to the questionnaire. And there's the formal welcome to the actual questionnaire. Hit the start button. Whereabouts are you in the house? In the living room? No, I'm actually in the study. I'm working hard on my PhD thesis. Thermal sensation, familiar 7-point scale, slider, easy. A few questions about other aspects or other adaptive opportunities. Windows are open, air conditioning is on, even a question on clothing. Just a very simple one. And that's it. That's it. So, officially, that animation took 59 seconds. And that was the goal. We wanted to design a questionnaire that would be completed in less than a minute. Because you have to understand, for these subjects, that it's a longitudinal research design. It means that we're going to ask them over and over and over. We had these people recruited to the sample for 2 years, or at least 18 months. So they got, I won't say sick to death of this questionnaire, but they got to know it really, really well. And amazingly, they stayed with the program. They didn't drop. We were expecting people to drop out because they got, absolutely, bored with the questionnaire. But no, they stuck with the program for at least 18 months, which gave us a great sample. We got summer data, we got winter data, and we got another summer data. Why did we have such a good response rate? And the answer is because the questionnaire was really short. I think the temptation of researchers all over the world is to put more and more questions into the questionnaire. It's an instinct. We just want to know more and more and more. So we had to really curb our enthusiasm, really keep that under control, because we limited it to 1 minute. We send out that text message at random periods of time. We put a curfew on the questionnaire. It's like an airport. We wouldn't go after 11 o'clock, and we wouldn't go before 6 o'clock in the morning. It would be intrusive to go into that nighttime period. So we put a curfew on the data, but there were certain times that we were very interested in, and the project that funded this was specifically interested in heat waves, in those rare occasions, maybe once or twice a year, where you have extremely high temperatures, because they're the ones that cause the biggest problem on the electricity grid because of peak demand through air conditioning. So during those episodes, when we were having a heat wave, we very, very specifically hit the send button several times, so we got as much data as possible. And we told the occupants, the respondents, that was the way it was going to be, and they were okay with that. But they might have got 2 or 3 questionnaires in one day, which was stretching the friendship just a little bit. So on average, it was about once a week, but on special occasions, 3 times a day, depending on the weather. And the duration of our survey was 18 months. So what I've described so far is the subjective side of thermal comfort research, how to get the perceptual stuff through a questionnaire. The next part of the problem, of course, is the objective, the instrumental measurements. And for that, we used a very, very affordable piece of technology. Not, I wouldn't say not laboratory grade. It's not incredibly accurate, but accurate enough for our purposes. We call it the I button. These little temperature measuring devices, as you see from the photograph here, it's about the size of a watch battery. It looks just like a watch battery. And it measures temperature with remarkably good precision. And you can select the precision. You can have better than 0.5 degree accuracy if you're prepared to have fewer measurements in the memory. But anyway, the most important thing about I buttons is A, they're very, very small and discreet. You can put them anywhere. And B, they're very, very cheap. They cost about $25 US each. At $25 a piece, we can put them anywhere or everywhere. We can put them all through the house. In not all of the rooms, but the main rooms that we were interested in. And so it becomes a very, very affordable piece of equipment. And they come in two varieties. There's a straight temperature eye button, measures nothing else, just temperature. It measures it at whatever time interval you want. We specified every 15 minutes. So we were logging temperature every 15 minutes. With every 15 minutes, we could fill up the memory in about 3 months. So it stores and timestamps 3 months of data. At the end of the 3 months, we have to go on site and extract the data onto our computers. But so that's good. It means that we only have to visit the people once every 3 months to sort of check on the equipment. Now, the second type of eye button, slightly more expensive, costing about $40 a piece, does both temperature and humidity. So in every one of our houses, we had at least one of these temperature humidity devices, because humidity is easy. You just measure it one place and you can generalize to all the other contexts. So that's how we did it, the temperatures. Now, another part of the research question was about how people were actually using the air conditioning equipment itself, when they're turning it on, how long it's on for, etc. And so, again, we just used eye buttons to solve that problem. We simply put one of these $25 temperature measurement devices inside the air conditioning system. And so, using some fairly simple logic, we can decide from the data in our eye buttons whether the air conditioning system is on or off. I won't go through all the logic here, but the basic idea is it's about when the temperature inside the air conditioning unit starts decreasing, the equipment's on, it's obvious. And especially when we compare that temperature change inside the air conditioning unit with the temperature inside the room. So we had eye buttons under furniture in each room, and we had eye buttons in the air conditioning registers of the equipment. So comparison between those two and the rates of change enables us to define when the equipment was turned on and when it was turned off. And it's so simple. Now, so I've described the comfort questionnaire and the instrumental data from eye buttons. There was a third source of data for each household as well. We call it a household questionnaire, and we collected basic information about the house itself and the occupants. So it included stuff about building physics. You know, what was the house constructed of? You know, how much glazing was there? Orientation, shade, etc., etc. We also collected some information about the demographics of the occupants, you know, age brackets, number of occupants, ages of the occupants, etc. We also collected some socio-economic data on the occupants, how much household income, what sort of education levels, etc. And then finally, some basic information on the air conditioning equipment that they've got installed. You know, the type of equipment, whether it's a split system or a centralized system or a window-mounted system, which rooms were actually air-conditioned, the capacity of the systems that they were using, the cooling capacity, the age of the system, which is going to affect the coefficient of performance, etc., etc. So we got all that information on the background. Now, I've actually spent maybe too much of my time describing the background of the project. And really that was my intention. I've got a few very early results. We've just got the data into an SQL database. And so the next stage of the project is basically to mine the database and start doing the analysis. So I'm not going to give you a lot of detailed results. I'll just give you a glimpse of the sort of things that we can do. First of all, just a few statistics about how much data we collected. 220 years of temperature data from 45 houses. If you add up the temperature records from each of the eye buttons and put it consecutively, one end to end, it would be 220 years of temperature measurements, and which represented 7.65 million data points. And accompanying that temperature data was 2,100 questionnaires on the iPhone, 4,900 air conditioning events, basically the air conditioning decisions to turn on, and cumulatively 11,800 hours of air conditioning use. Residential clothing, you can see a clear seasonal pattern there. The purple represents the heavier clo value of 1, and it's obviously peaking in the winter. Again, you can see some obvious patterns in the way in which the air conditioning equipment is being used. You can see the cooling mode during summertime and the heating mode during winter time, and obviously the months of April and September being the months in which the air conditioning equipment is least used. Some interesting results on the air conditioning duration, how long the equipment is actually being used for. And we were kind of surprised, and I'm still not 100% convinced that this is accurate, but it looks like it's very common for people to turn on the equipment for short duration, for short periods of time. We were expecting that people would just turn it on and leave it on permanently, but in actual fact, it seems like people are using it just for short periods, maybe coming home from work, finding a hot house, and then chilling it down, and then switching it off. So you can see that's true. That's particularly true in summer. In winter. They use the heating mode for short periods of time. Most of the observations occurring less than 1 hour. We've got interesting data on the time of use of air conditioning. Time of air conditioning use, and this becomes particularly relevant to the issue of electricity demand and the timing of that demand and how that relates to peak demand on the electricity grid. But you can see clearly that the most heavily used period in the day for air conditioning in both cooling mode and in heating mode was in that period from 4 o'clock in the afternoon until midnight. So after work, basically. That's when heating and cooling is most typically used. But you can see some differences between these two. In the cooling mode, the next most frequent period is the 10 o'clock to 4 o'clock period. But in the heating mode, the next most frequent period is in the morning, from 6 o'clock to 10 a.m. So people using the heat pump basically to just take the chill off the house after waking up and then turning the equipment off when they go to work. One of the interesting aspects of this whole project, and one of the drivers that I haven't mentioned, is for the benefit of the thermal simulation people. In the audience, particularly in engineering audiences, we have a lot of research using energy simulation of houses. And in that software like Energy Plus and Design Builder, there's always the requirement for some behavioural stuff. We call it occupancy schedules. And somewhere in that setup of your simulation of Design Builder or Energy Plus, there's going to be a question as to at what temperature do people start turning this equipment on? And yet the answer is pretty typically based on an assumption. Maybe it's based on a P&D calculation. And so the question is, well, what is the temperature that prompts people to turn on air conditioning? So we've got a technique here that can actually give an empirical answer to that question. And we do it by Defining the point in time when the equipment got turned on, that's easy. The I button tells us that. Stepping backwards through time, 15 minutes, we can see from the I button in the occupied zone of that room what the temperature was. And we're going to assume that that was the temperature that triggered the decision to turn on the air conditioning. So if you follow that logic, this is what we found. The heating trigger temperature most typically was in the region of 16 to 18 degrees Celsius, and the cooling trigger temperature was most frequently in the 26 to 28 degrees Celsius range. Now, for the cooling decision, which is maybe of more interest to me in my research activities, that number is actually higher than the number that most typically you find in the behavioural schedules of your Energy Plus simulations. It's typically going to be 24 or 25 in those simulations. So we learned something here. And so I expect that these results will be of use to energy simulating researchers. I'm not going to show too much more detail about the adaptive model. I really have run out of time. But here's a distribution of cooling trigger temperatures. So we're talking about summertime observations. And you'll see that the distribution of cooling trigger temperatures is about the same in the daytime as it is in the nighttime. But in heating, a slightly different story. In heating, we find that the morning session, the cooling trigger temperatures are lower, and in the evening session, the cooling trigger temperatures are higher. So we're really just scratching the surface of these data. We've got lots and lots more to do, and it's going to be fascinating. I won't go into great detail about bedroom temperatures today because, as I say, I've kind of run out of time, but for the first time, we're finding information about how people use air conditioning in their bedrooms. Nobody's done this work before because the techniques haven't been available. In Singapore, just by contrast, in a hot and humid climate like Singapore, we've heard anecdotally that people are sleeping under feather eiderdowns. In a hot, humid climate, they sleep under feather eiderdowns because they've got air conditioning in the bedroom. And they can push the air conditioning temperature down to 17 or 18 degrees Celsius and then pretend that they're living in a cold climate. And they say that they get a better night's sleep. So this technique enables us to explore those sorts of issues. I'm going to jump forward and just these next two slides, and then I'll wrap it up. This is an interesting one. From my point of view, theoretically, this is a very interesting set of data, and it shows average thermal sensations in the living rooms. And you can see, without air conditioning, when the house is actually running in naturally ventilated mode, that thermal sensation goes up as temperature goes up. So thermal sensation in the range of 23 to 24 degrees is very close to neutral. From 24 to 25, it's sort of getting up towards halfway. From 25 to 26, it's halfway between neutral and slightly warm. And from 26 to 27, it hits almost slightly warm. So it's doing what we would expect. People vote warmer as the temperature gets warmer. But look at the responses on the air conditioning stage, part of the sample. So here we've got people who've got air conditioning running in their living rooms, and in that temperature range, 23 to 24, they're saying that they're slightly warm. It's the same temperature as they had when it was naturally ventilated, but they say that it's one whole thermal sensation unit, warmer. What's going on there? There's something strange. 24 to 25, also slightly warm. 25 to 26, about the same. There's hardly any movement. 26 to 27. And the numbers that you're looking at here are the size of the samples, just to give you some sense of, we might say that, oh, you had very small sample size, so the number's not that accurate. But for most of these numbers, we're talking about fairly substantial sample sizes. 26, 35, 22, 19. So this deterministic logic, physics impacting the physiology of the body, impacting the perceptual psychology aspect of the problem, and then affecting behaviour, it doesn't seem to work. It seems to be logical in the naturally ventilated sort of mode, but in the air-conditioned mode, it's not quite as you would expect. It's almost, and this is just speculation, I admit it's just a speculation, but it's almost like people have made the decision to run the air conditioning and then they've adjusted their thermal sensation to suit the behaviour. The logic is going backwards. It's very strange. And this is the worry with air conditioning in homes. People, once they buy the equipment, which is very cheap, once they've bought it, they're going to use it. Even if they need it. Even if they don't need it, they're going to use it because it's there. This is what we find. So, I think all of this presents some very fascinating possibilities in Brazil. As Brazil embarks on the journey of air conditioning the residential sector, it's going to be, I think this sort of research would have considerable value. So a few very, very basic conclusions. One is context matters. It's not the same in offices and it's not the same in other environments. Context is relevant. Deterministic comfort logic is not that relevant either, because the occupants are not 100% rational. I'm not going to say that the occupants were irrational, but let's just say not 100% rational. And I think that's about all. So I'll finish it there with a little animation of a camel that we met in India at Plia. I think some of you were at Plia, or at least there's a very nice conference back in December last year. But, so thank you for listening, and I'll open the floor to questions.